Good morning, good afternoon, good evening, depending on where you are. I would like to welcome you to webinar 21 on CPT, in this CPT series that is organized by Eijkelkamp North America. And the topic for today is CPT and soil improvement. You may wonder why I now show you this thing about webinar number 19. It's not January, and this was webinar number 21, but right now we are kind of a series of webinars that deal with certain applications. How can you use the CPT data? Initially, we covered what CPT was all about, what kind of data you get, but right now we're more in a series that talks about how you can apply CPT for certain applications. And in January, we covered CPT and groundwater, which was then followed last month with CPT and then pile driving. And shortly after I gave that presentation, somebody came to me, said, listen, it's very interesting that you talked about pile driving, but what I'm really interested in is how you can apply CPT when it comes to soil improvement. So that's the topic for today. And we're going to look at what the CPT testing method, the cone penetration testing method, can do when you're talking about soil improvement. The first question then that comes up is, what is soil improvement or ground improvement? And when I put these slides together, I had to kind of smile because it reminded me of something that happened when I was teaching at the University of Texas many years ago. On one of the exams, I put exactly the same question. And I got an answer from quite a few of the students saying, well, ground improvement is a method or technique to improve the ground. While that is true, and I could not really fault them for giving me that answer, that was not really what I had in mind. What I had in mind was more something like this, that we improve the behavior of the ground, or the behavior of the soil, because that is really what ground improvement aims to achieve. And when you think about that, when you talk about soil behavior or ground behavior, automatically you start thinking, well, if that's the case, then hey, that has something to do with CPT. Because after all, CPT talks about the ground behavior, the soil behavior. So there must be a link, and that's why the question marks on the left turned into some light bulb came on. That there must be a link how you can apply CPT when it comes to soil improvement or ground improvement. And then, of course, the graph that you see now, the bottom of your screen, that has everything to do with it. Because for those of you that are not that familiar with CPT, as you push the cone into the ground, you get those three squiggly lines, as Paul Main refers to. The tip resistance, the sleeve friction, and then the pore pressure. But when we take the first two, you end up with a graph that you see at the top left-hand corner, where you take the tip resistance on the vertical axis and you get the friction ratio on the horizontal axis, which is nothing more than the sleeve friction over the tip resistance, and you define then a number of fields, a number of areas that, according to Robertson and Campanella back in the 1980s, are classified as certain soil behaviors. Not, as said before, not what the soil is, but how the soil behaves. And then on the right-hand side, we do the same thing again independently, but now for the tip resistance and the pore pressure. And you get the same 12 fields, and hopefully the two correlate and you get the same conclusion. But it describes how the soil behaves. So going back then, when we are talking about ground improvement, how you try to do something to improve the behavior of the ground, CPT must be a good method for that. It must give you an indication, because you should be able to see that then when it comes to the soil behavior on your chart. So those things must match one way or another. And that's what is indicated in this conclusion. So what are some ground improvement techniques? Well, here I've just listed a few of them to give you some kind of first indication what's happening there. Of course, you can preload or surcharge with sand. as you see in the bottom center. And then you can either let the groundwater kind of seep out, or you can make it a little bit easier by applying vertical drains, whether Vic drains or sand trenches, whatever you want to do it, as you see that indicated by the black arrows. The black arrows in the left-hand side, obviously the water has to escape through the top. And then on the right-hand side, what you can do is that the groundwater penetrates horizontally to those wick drains or those vertical drains, and then through there come to the surface. But that's not the only ground improvement method that we have. Yeah, you can do compaction, as is indicated on the bottom left. And there are all kinds of different compaction techniques. We have dynamic compaction, we have vibratory compaction, all kinds of stuff, all kinds of techniques that will kind of densify the soil. And then, of course, you have soil removal and replacement, use of stone columns or encased sand columns that you see illustrated on the bottom right-hand side. And then a fourth technique that I have not indicated or illustrated with a graph are in situ mixtures, deep mixing with lime or with cement or with fly ash to again increase the strength of the soil. Now, I'm not saying that with CPT you can actually identify which soil improvement method you have applied, but it does tell you something about what is happening with the soil. Because as you're going with this whole thing, you can figure out why ground improvement is really carried out. And there are really four aspects that I want to focus on today. First, probably foremost, is that you want to improve the shear strength of the fill and the subsoil so that you have sufficient bearing capacity. Now, that's one of the major things that you are trying to achieve to improve the strength of the soil. The other thing, the second one, is to improve soil permeability. As you're putting those vertical drains in there, you make sure that you increase the permeability, therefore increase the drainage capacity so that you can get rid of that excess groundwater. And that's what the wick drains or the vertical sand drains are all about. The third objective is to increase the density of the mats or the subsoil. Again, densification, it not only improves the shear strength, but it also will help you to prevent liquefaction. So that's a third objective that you have as you are trying to do your soil improvement. And then the fourth element is to prevent excessive settlements. If you are doing your ground improvement, if you are in an area where you can have major settlements, you can do things to make sure that once you have the soil improvement applied, that those settlements are going to be reduced. So those are the four major objectives for ground improvements. And different methods can be utilized more or less efficiently to achieve those objectives. But let's focus just on those objectives. And as you have seen in there, I've put some of those words in red on purpose, because those elements, whether it's shear strength or permeability or density or sediments, are absolutely perfect concepts that you can check with CPT. And that's really what I'm trying to convey to you today. Let's first look at the shear strength. I have to give you a few equations, and I'm not saying that you're going to, after this, there won't be an exam that you have to learn all these equations or be able to regenerate these equations. But when you look at the shear strength, it is really a function of the tip resistance minus the total in situ vertical stress, and then divided by some empirical cone factor. There's not a one-to-one, very clear equation that you can use, and because there's this empirical cone factor, but there's a very good and solid correlation between the shear strength and the tip resistance, Q sub C. So that means that if you're trying to do a soil investigation, you can push your cone, figure out what your tip resistance is, then do your soil improvement, push the cone again, and you should see a clear increase in your tip resistance and subsequently in your shear strength. Therefore, it should come as no surprise that if the objective is to improve shear strength, that the CPT method is a very good soil investigation method to monitor that, to control that, and to check that you have made sufficient improvements. Before we go any further, though, one thing that I would like to emphasize is this book that I've mentioned to you in previous webinars as well. It's a book written by Peter Robertson, A Guide to Cone Penetration Testing. You can find it on the internet. There are all kinds of websites that have this book. It's free, which is another nice thing. But what is happening in this book? Peter has put together a whole bunch of correlations when it comes to CPT data and then various soil parameters. And you see in there the force from the top on the left-hand side, the undrained shear strength, the SFU, and that's the equation that I showed you as well. So if you want to know more about these equations, if you want to get a little bit better feel for the equations that I will mention in this webinar, this is an excellent source. And then, of course, there's lots of other correlations that Peter covers in his book that I will not mention today, but they may come up in other webinars, or they have come up in other webinars. But let's go back to what we were talking about. Shear strength we've now covered, and we've seen that CPT is a good method to figure out what the shear strength is, and therefore a good method to figure out how you can improve your shear strength. So what about permeability? What you see there on the left-hand side is the surcharge with a preloading, and we have applied some vertical drains. But the main thing is that we have to figure out, what is this horizontal movement of the water towards the vertical drains, because that will determine the effectiveness of what you're achieving. Well, Barron and Eijkelkamp developed back in the 1940s an equation that really describes how you can come up with this permeability and how you can describe the whole process that is going on there. And as you can see in that equation, there's a term in there, C sub H, which is the horizontal coefficient of consolidation. And then the question is, what is that and how does it relate to CPT? And for that, I would like to go back again to the slide that I showed you already earlier, but now focus on, again, the one on the very right, the pore pressure. What we measure during CPT is not necessarily the actual hydrostatic pressure, but it's the dynamic pore pressure. It is the pore pressure that is affected by the cone, by the dynamic movement of the cone, and therefore you have an excessive pore pressure well in excess of the hydrostatic pressure in most soil conditions. But over time, if we were to stop the CPT test, if we were to leave the cone in place, that excess pressure slowly dissipates. And that's part of the dissipation test that was covered in one of the previous webinars. And what you see on the graph on the left-hand side is how over time slowly that pressure dissipates from the starting pressure to, in the end, the hydrostatic pressure that you have there. Now, if we know what the total curve is, or if we already know what the hydrostatic pressure is, we can figure out how much time it takes to dissipate half of that excess pressure. And that's the so-called T50, when 50% of the excess pore water pressure has dissipated. And the T50 gives us a very good correlation with the hydraulic conductivity. As you see here, on the horizontal axis, you have the T50. On the vertical axis, you have your hydraulic conductivity. And you see that while there is a bend, it gives you a very good indication from the T50 what your hydraulic conductivity is. And it so happens to be that the hydraulic conductivity gives a good indication of the horizontal coefficient of consolidation, C sub H. Once again, it's not perfect. It's not a one-to-one equation that you can do and you get exactly the answer, because as you can see here from the T50, there's a range in values of K, and therefore you're going to get a range of the values of C sub H. But there's a very good correlation. And that means that, again, if you see that your hydraulic conductivity, you can approximate that with your CPT, therefore come up with an approximate value of C sub H, and then use the equation that I showed you earlier to figure out what your overall permeability is going to be and what the effects are going to be. So once again, CPT is a good way of testing and utilizing that to figure out how your effectiveness of your ground improvement is. So once again, the check mark. Then when it comes to the density, I don't want to give you the equations necessarily. And again, in the book that Peter put together that I showed you earlier, he puts a paragraph or a section on that as well. But research has provided numerous correlations between CPT penetration resistance and the relative density, especially in sands, in the granular soils. And when we're talking about increasing the density, when we're talking about compaction, most of the time we do that in granular soils anyhow, because it's very difficult, if not impossible, to really compact the cohesive soils, at least not with compaction. And that brings me, first of all, the conclusion is again that with CPT, we can figure out what the density is, and therefore it's a good way of calculating this. But I want to also point out something else that comes back time and time again. Sometimes people say, Gerald, yeah, I understand that you're a cone head. I understand that you believe that CPT is a very good soil investigation method, but it's not perfect. And I say, I'm the first to agree. It's always important that you identify what you don't know. And the reason that I wanted to bring it up here is when it comes to compaction, there is something that we really don't truly understand. As you apply compaction, as you do the soil improvement, you can say, okay, you test the soil beforehand, the unimproved or the virgin soil, then you do your compaction, whether it's fiber compaction or dynamic compaction or do some blasting on this whole thing. Yeah, all kinds of different compaction methods. After you're finished with that, you check again, and then you would see an improvement in your tip resistance. Very true. But then, so that part we understand. That's logical. But what research has shown, as you see in these graphs here, is that when you then go and wait for this whole thing, where you on the vertical or the horizontal axis is the number of weeks that you wait there, and it's on a logarithmic scale, you see that compaction seem to have a continuing effect. Kind of like with setup on pile foundations, you see that after a number of weeks, you're going to have after about, say, 5 weeks or so, 4 or 5 weeks, you end up, in case of fiber compaction, about 1.5 times more tip resistance than what you had right after the compaction has been completed. Now, with setup and pile foundations, that is at least, we can explain that because of a change in pore pressure. In this case, even when there is no change in pore pressure, even when at the surface you don't see anything, there's no settlement, somehow the soil still improves and its strength and its tip resistance. Do we fully understand it? No, we don't. And that's something that we need to identify and make very clear that there are limitations in our understanding where we still can learn more, but I'm not aware of any clear explanation why this is happening. Which also brings me now to the last point, because as I go back to this one, you've seen that I've covered in this webinar shear strength, permeability, and density. And I've shown to you how those parameters can be very well checked with comp penetration testing. The last one, settlements, is something that if I start talking about that in the remaining time that I have, and I have roughly 7 more minutes in this webinar, I would have to stop halfway in between, or be barely started actually. And that's why I've decided that we will cover that in the next webinar when dealing with CPT and soil settlement, not just when it comes to the part with ground improvement, but with settlement in general. So with that, I've come to the end of this webinar, at least what I had prepared for you today. Hopefully, I've made clear to you that when it comes to ground improvement, when you are trying to change the behavior of the soil, to make it more suitable for whatever you want to do in that area, that CPT is a test method that will help you to give an assessment, an indication of how well you've done that ground improvement. And once again, you get with CPT instantaneous results. And that means that as you go to a job site and you do your CPT, you immediately know whether the increase in the shear strength or the compaction aspect of the increase in density, whether it meets your requirements, and if not, then you can do additional compaction or decide that maybe something else is going to be required. Time for a few questions. The first question that I see here, and I will try to. Fiber compaction, normally used in land reclamation. After time, can the sand become cemented due to salt water when rainbowing and temperature effects? Cementing over time can absolutely occur, but it's not something that is going to happen instantaneously. And when you are doing your compaction, normally what will happen is you do your testing right after your fiber compaction. And the effect that I showed you earlier, that with fiber compaction over time, over long periods of time, that you see an increase in the pore or your tip resistance. I don't think it's necessarily it's explained by cementation, because that cementation doesn't necessarily occur all that quickly. But indeed, over time, over long durations of time, you are going to see the effect of cementation. After all, when you are looking at the soil behavior chart and you go to the top right-hand corner, over-consolidated or cemented soils are in there as a separate area. The second question that came up was that it may be due to secondary settlement, the increase in your tip resistance as a result of deep compaction, maybe due to secondary settlement, creep, or simple rearrangement of the soil structure. Well, the problem is that all that may be part of the whole thing, but as you already put it out in your question, you talk about settlement. And we have seen this kind of increase in tip resistance without any settlement in the soil, without any change in pore pressure. So it's a complex issue that is really not all that easily understood or explained. And then finally, the person that actually asked me for this or suggested that I gave this presentation asked me that will this presentation be available for review after the webinar? Absolutely. Like all other webinars, you can find on the Eijkelkamp YouTube channel. When you go to YouTube and you type in Eijkelkamp with the name that you see there on the top left-hand corner, you go to the Eijkelkamp channel. And if you then scroll down, you will find webinars. And in there, you will find all webinars, all 20 ones that we've had before. And surely by the end of this week or early part of next week, this webinar will be posted as well. With that, I have about everything that I have time for today. So I want to thank you for being here. I hope you found this useful, and I hope that you at least are now seeing that CPT is a good test method that can be used to assess the effectiveness or the extent of the soil improvement. So thank you very much, and I look forward to seeing you next month. Thank you.